Yes, good afternoon. How are you today? Good, Emre. Thank you so much. I am so fine. Yes, we didn't finish our subject the last week, I think, and we were stopped anywhere. Do you remember? We was doing the chemical compounds, you know that, and before starting the lesson, I want to say something about email. I sent the email to you, all of you from the OIS. Please check it, okay? About the laboratory, you know that from the last week, because I explained all of that, and I think Bihter said all of you, and there are only how many students? Just a minute. How many students? I think 10 or 9. Yes, 9 students we have. Yeah, we are gonna do our laboratory experiments, and also I will send all of these experiments in the system, and you can watch all of that. Yes. Do you remember where we were? I think ionic compounds. Is that right? Or I think I showed these balls, the color balls, and while we draw the molecular models, we use these balls. For example, the black one shows us the carbon element, and or the red one, red or pink, maybe this is the oxygen, and the boron is the light red. Yes, do you remember ionic compounds? I think, is that right or not right? Please say anything about that, where we were. Do you remember or not remember? I think ionic compounds. Hi, all of you are here or not here? I am asking a question, but you don't answer anyone. Yes, Abdel Monian. Yes, Nada. Do you remember that we were here? Ionic compounds? Yes, that's right. Okay. So let's start. Yes, ionic compounds. You know that this is the ionic compounds generally is made up a positive. Yes, positive and negative ions joined together, and electrostatic forces of attraction. Generally, we call that this is the attraction of oppositively charged objects with, like that, for example, the sodium atom, and sodium atoms, you know that this is the metal, and always he wants to give its electron to the another, each one. This is the which one? This is the, yes, chlorine atom, and always the chlorine, this is the non-metal, always wants to take the electron from the other, which one, what's that? This is the metal ion, and they appear any ionic compounds or ionic bonds, we can call that. The atoms or metallic metals tend to lose. You know that from the last week, and always I said that one, and more electrons always tend to lose when they combine with non-metal atoms, and we call that these compounds molecule is ionic compounds. Don't forget that. And non-metal atoms tend to gain, one or more electrons. As a result of this electron transfer, the metal atom becomes a positive ion, or we can call that the cation. Okay, don't forget that, it's the cation one, positive ion, and the non-metal atom becomes a negative ion, or we can call that this is the anion. Okay, don't forget, these are very important, cation and or anion. Always I will use these terms. In the formation of sodium chloride, this is ordinary table salt, you know that. Each sodium atom gives up one electron to become a sodium ion, and each chlorine atom gains one electron to become a chloride ion. Okay, this is the ionic compounds, don't forget that. And ionic compounds combination is cation and anion, don't forget that. Yes. Other slide. Oh, really? The mole. The mole. We did this part. We did this part. Really? But you said we. But you said to me we didn't. We stop here in the ionic compounds. You said, Victor. The others. We did here. Yes, I remember here. Yes, we did here. I remember that. Yes, Victor, you are right. Here we did that. Didn't we, Victor? I think you remember. Right, we did. Okay, I think I gave this homework to you, and then I think we stopped here. We didn't do that. Yes, Victor, thank you so much. I think you followed my lessons, only you follow. So, not good. Thank you so much, Mr. Yes, example, the volatile liquid ethyl mercaptan, and these molecules formula is like that. This is the carbon, 2 carbon atom, 6 hydrogen atom, and only 1 sulfur atom. Is one of the most odoriferous substances known because of the sulfur. Sulfur is so odoriferous, and this is so bad because, for example, in the middle of the egg is the yellow color because of that sulfur. So this smells not good. And you know that from the first lessons, I showed you the sulfur is the yellow color. Do you remember that? I wish you remember. It is sometimes added to natural gas to make gas leaks detectable. So this is this smells so bad. How many these liquid ethyl mercaptan molecules are contained in a 1 microliter sample? The density of liquid ethyl mercaptan is 0.84 gram divided milliliter. While we finding these molecules, if these molecules are liquid, we always use the liquid's density. The density is very important to convert milliliter from milliliter to the gram, because we don't we can't weight this liquid with the gram unit. Always we weight this liquid milliliter or microliter or liter. Okay, don't forget that. So always for the liquid substances we use the density. And what does it mean? That means 1 milliliter is 1 milliliter equals 0.84 gram for this ethyl mercaptan. Okay, ethyl mercaptan, because of this liquid substances, 1 milliliter equal 0.84 gram. Okay, and then we have only 1 microliter. 1 microliter. 1 microliter. How many milliliter we have? How many milliliter? You know that? Do you know? This is the conversion, microliter, milliliter, or 1 milliliter is 1 milliliter equals how many liters? What is that? Please tell me about that. Yes, I'm waiting. Mariam said 0.01. Yes, what about? Anyone else don't know? Bihter 0.01. What about the others? Why all of you said 0.01? Yes, you are right, Suleiman. Thank you so much. The others not right, because this is yes, that's right. This is only you have to divide it 1000. Don't forget that. You have to divide. You should divide 1000, and that means 10 negative 3 milliliter, or we can say that 0.00 is 0.01 liter. Okay, this is the same thing. And they said us this is the microliter, and we should this microliter from microliter to the milliliter. So we write here 1 microliter is equal, this is 0.001 milliliter. Okay, and then let's doing that problem with the proportion. 1 milliliter equals that gram, but we have that milliliter, 0.001 milliliter. How many gram we have for the ethyl mercaptan? Okay, don't forget it is the x we can write here. The x means 0.84 multiply with like that. This is the gram one. Okay, and then we find this gram, but they ask us how many ethyl mercaptan molecules. If they say us like that, this is the molecules, they want us which one. We follow this calculation with the gram, or we should find another unit. Which unit we have to find from the gram? Can I find these gram units to find the molecules? Yes, I'm waiting your answer. Yes, we find this gram, and then can we find the molecules from the gram? Yes, say something, please. If you are here, say something. You can say, I don't know, I have no idea. Please tell us. If you hear, say. Okay, Habib, you don't know. And molecules. While we said the molecules, you have to know what? We can convert grams to moles. Yes, we have to convert these grams to the moles, and then we can find the molecules. Because if we want to find these molecules, we have to know the moles. Okay, so you know the mole formula. You know the mole formula. This is the M. This is the gram mass. And then this is the molecular mass, and you have to calculate that formula, molecular mass, and always I will give you these atomic mass. For example, carbon is 12, and hydrogen is 1, and sulfur is the 32. Okay, gram divided mole, all of that gram divided mole. And then you have to calculate that ethyl mercaptan molecular mass, and you will find 62.1, okay, gram divided mole. And you know this mass, and put this gram from here, and then put that molecular weight here and calculate. While you calculate how many mole you find, please do that. Actually, you're right. Yes, this is the 1.4. Multiply that 1. This is the mole ethyl mercaptan. Okay. We found that, and you know here 1 mole, always all of molecules, 1 mole contains Avogadro numbers. Okay, always 1 mole ethyl mercaptan, Avogadro number, what is that? This is 6.02. Multiply with that 1023 molecules, but you have that mole, and you put that here. 1.4 multiply with that mole, how many molecules? And you will find 8.1 multiply that 1018 molecules. Molecules, what's that? Ethyl mercaptan molecules. Do you get it? Is that clear or not clear? If you want any explanation, I can explain. You don't understand, Suleyman. Is that right? Where you don't understand, you can say, or the beginning, or is that clear? Miriam said yes. Raymond, is that clear? You said no and yes. I can't understand. And then I will pass that slide. The conversion and finding the gram per mole. Yes, the conversion, that conversion, you have to know all of these conversion, okay, from the first lessons, or you have to know that. And then this is our formula about the mole. You have to know that, and I explained that mole and Avogadro number the last week. You should remember that from the last week. Please, okay, please always do that again and again. And you don't understand anything about my recordings, please ask me for the email. But here, here where you can't understand, Süleyman, I said the conversion you have to know, and this one you have convert that and molecular mass, and also I will give this atomic mass, and you have to calculate that molecular mass you will find, and put this value in our formula, and you will find the mole. And then you know that 1 mole molecules always 1 mole, any one molecule, this is carbon monoxide or water or ethyl mercaptan, all of the others have these molecules, okay, that molecules. But you have that mole, how many molecules you have, that's it. Okay, I will pass, the time is going. This is your homework. The gold has the density. The density is important, and you will did this homework with your maths. Okay, with your maths, very important. This is the gold foil, the centimeters, and each side and meter thick. This is our. This is about your maths, not the chemicals. Yes. Okay. Composition of chemical compounds. The molecular formula tell us that per mole of halotene, for example, there is a halotene, there are 2 moles of carbon atoms and 1 mole each of hydrogen, bromine, and chlorine atoms, and 3 moles of fluorine atoms. This factual statement can be turned into conversion factors, and this is generally we will do that. The other examples with these liquid halotene, and generally we did this while we find this molecular mass, we use that the 2 mole carbon atoms, so we have to multiply the 2 with this atomic mass, and then the hydrogen, bromine, and chlorine, each of atom is only 1 mole, so 1 multiply with these all of these atoms atomic mass, and then the fluorine only 3 mole, and you have to multiply with this fluorine atomic mass with that mole, 3 mole, and you can find this molecular mass, the halotene. And then yes, for example about that, how many carbon atoms are present per mole of halotene? You know that halotene formula. Here I will give you, this is the halotene, hydrogen, bromine, chlorine, and fluorine one. And you know that how many carbon atoms, okay, how many carbon atoms are present per mole of halotene? You know that 1 mole molecule has 6.02 that Avogadro numbers molecules, but you have 2 mole carbon atoms, okay, 2 mole carbon atoms, how many carbon atoms you have, and then only you have to multiply with that Avogadro numbers with these carbon, the mole of the carbon, and you will find that carbon atoms. Yes, the other one, the example of that, how many moles of fluorine atoms are in a 75 milliliter sample of halothane? The halothane is this liquid substances, so we should use this density because the density tell us the milliliter and gram. Between the milliliter and gram conversion. This is very important, and always that tell us 1 milliliter is liquid 1.871 gram. Okay, but we have that milliliter. That milliliter halothane, how many gram has? We have to multiply that. Just a minute, I calculate here. Multiply with 75. Yes, 1040.325 gram. Okay, this is only, yes, Mariam, this is only gram, but they ask us how many moles of fluorine atoms. Okay, how many moles of fluorine atoms? So you have to convert that from gram to the mole. So you write here, and you know that the mole, the halothane molecular mass, you know that this is 197.4 gram divided mole, and you will use the formula, or you will use the proportion what you want, and this is gram of halothane, and this is molecular mass of halothane, and you will find the halothane mole, yes, divided with 197.4. Yes, this is 0.71. 0. Yes, thank you. Moles. This is halothane mole, but they ask us how many fluorine atom we have. Okay, so you have to, you know that this, yes, this is the bromine, chlorine, and fluorine. You know that this is the fluorine atom. 1 mole halothane atom, 3 fluorine atom we have, but here 0.71 mole. How many fluorine atom we have? Okay, and then you will find this is 0. Just, yes, yes, I think the same value we will find. Yes, that's right. This is 2.13 mole fluorine we have for that halothane. Do you get it? Is that clear? Only you will do the conversion only, and by using proportion or by using formula. How we get 3? We get 3 from the formula. Amir, from the formula we have that fluorine atom 3 moles. So we multiply with that mole with these 3. Okay? Okay or not? Okay. Yes, Yes, only first of all, convert the volume of the sample to the mass. And this requires density as a conversion factor. The conversion factor very important. And then the next one, convert the mass of halothane to its amount in moles, and this requires the inverse of the molar mass as a conversion factor. And the final conversion factor is based on the formula of halothane. That's it. Yes, this is your homework. And then this is important. Yes, this important subject of the chemical substances, calculating percent composition from a chemical formula. We will find how the mass percent of an element in a compound is calculated, applying the equation and thinking the terms of these following steps. For example, first of all, determine the molar mass of the compound. You don't forget that. First of all, you have to determine the molar mass. And then the second one, determine the contribution of the given element to the molar mass. And this product of the formula subscripts is very important. Subscripts always give you the moles about the atoms of the molecules. And the molar mass of the element appears in the numerator of equation. And then the third one, formulate the ratio of the mass of the given element to the mass of the compound as a whole. This is the ratio of the numerator from step 2 here to the denominator from step 1. And then the final, multiply this ratio with the 100% to obtain the mass percent of the element. So if you want to mass percent element, that is number of atoms of element per formula units, multiply with the molar mass of element, and then divide it with molar mass of compound, and for that calculate, multiply with 100. Let's doing an example, and then you can understand easily while doing this example. What is the mass percent composition of halothane? For example, for the carbon, hydrogen, bromine, chlorine, and fluorine, we want to find all of these atoms percentage. And for example, for the carbon atom, percentage carbon is equal how many moles of these halothane carbon atoms contains? Only 2. 2 multiply with that's carbon atoms atomic mass, and then divided all of these molecules molecular mass. Okay, and then multiply with 100, and you can find the percentage of carbon atom of this halothane contains. All of these atoms doing the same thing, only you have to be careful here. How many carbon atoms in that halothane, how many hydrogen, how many bromine, how many chlorine, and how many fluorine atom you have. And for example, for the bromine atom, only 1, don't forget that, and you have to multiply with this bromine atomic mass, and then divided this halothane molecules molecular mass and multiply with 100, and you will find the 40.48% of bromine. This is only 1 bromine we have on the composition of halothane, but the much more percentage is bromine atom, because of this is atomic mass. This is only 1, but this percentage is very much more than the others. For example, fluorine atom is more than the bromine, because the fluorine atom only 3, but this is bromine 1, but fluorine atomic mass is smaller than the bromine atom, so the percentage is lower than from the bromine. For example, check that here, the bromine percentage 40, but the fluorine percentage 28, although this fluorine moles is bigger than the bromine atom. Do you get it? I think you get, because of this atomic mass. And then if you want to control that halogen, you can collect all of these percentage that approximately will be 100. Okay, please, can you check that percentage? Collect all of this percentage of this atomic value. Please check and set to me. Yes, first of all, we determine the molar mass. So I am waiting your answer also, and then I will explain something about that calculation, and I am waiting your answer. Okay, please check that. Only 100. Yes, that's right. This is so cool. First of all, determine the molar mass of halogen, and then formulate the mass ratio and convert them to mass percents. If we use molar masses that are rounded to 2 decimal place always, the calculated mass persons may be accurate to the 2 decimal place. We can write here the 2 after the point, 2 decimal numbers we will use only. Yes, this is your homework. This is your homework. This is adenosine triphosphate. This is ATP. This is very energy storage for us, for our molecule in our cells. And this is molecules will be here. And then will be like here. There are carbon, hydrogen, nitrogen, phosphor, and oxygen atoms. Please, while you are doing these examples, you have to check your periodic table. Okay, you will use this atomic mass from your periodic table. Don't forget that. You cannot do anything if you don't use any these atomic mass. Okay, you have to check the periodic table. Yes, for example, the percentage of the elements here in a compound should add up. This is 100%, and we can use this fact in 2 ways. What is that? This is, first of all, check the accuracy of the computation by ensuring that the percentage total 100%, and as applied here, the results here, you did that, and you found 100, and then the determine percentage all of the elements, but one you don't know. So, for example, you know the carbon, bromine, chlorine, and fluorine, but you don't know the hydrogen atoms percentage. What you will do? 100 minus with all of these elements and then you can find easily that you don't know how many percent of hydrogen atoms easily. This is only maths. Yes. Establishing formulas from the experimentally determined percent composition of compounds. This is very important thing. For example, I will give you some gram or some percent of the atom mass, and you will find the real molecule formula or unreal molecular formula you will find. For example, here there is a which molecules? Yes, 2-deoxyribose, a sugar, you know that from the DNA, and that is a basic consist of DNA. Yes, deoxyribonucleic acids, sugar. The mass percent composition of 2-deoxyribose is 44% carbon and 7.52% hydrogen and 47.71% oxygen. And if you want to find these 2-deoxyribose sugars molecular formula, you will use all of this percentage, okay? And then you can think that this percentage is approximately equal the gram of carbon, hydrogen, and oxygen. You can find that. And while you collect all of these percentage, you will find the 100%. Yes, and then you can think that this is the gram. Okay, first of all, although we could choose any sample size, if we take of one of exactly this is 100 gram, as I said, the masses of the elements are numerically equal to their percentage. Okay, you can think that. And this is the carbon atoms gram, and this is the hydrogen atoms gram, and this is the oxygen atoms gram. And if you want to a molecular formula, you have to find the mole of these atoms mole. So you can find the moles formula. You know that this is what is that? This is N is equal M, and then this is the molar mass, or you will use this is what's that? This is atomic mass, and this is the what's that? This is, you can think that percentage. What is that? This is, for example, the carbon atom, 44.77 gram divided. What is the gram atomic mass of the carbon atom? This is the 12, and you will divide that value, and then you will find the mole of carbon atom. And the others, for example, hydrogen atom, you have to divide it to 1 gram, and you will find. And for the oxygen atom, you will do the same thing, and you will find that one. And if you want to use that moles, you have to write these values, the atoms subscript. For example, carbon atoms, how many moles we find? This is 3.727 mole. And then for the hydrogen atom, this is the 7.46, and for the oxygen atom, you will find this is 2.98 and 2 mole. You have to do that. This is not the molecular formula. Yes, that's right. This is not the. Just a minute, Emre. Okay, I will explain that. For the molecular formula, this is, yes, always. First of all, always you will find the empirical formula, not the real formula, okay? And then if you find like that, this is not Yes, here. This is not the chemical formula. You don't see any books or any the others file. You don't see that like that. You have to these numerical exact formula, not the tentative formula. Okay, and then you have to divide it. You have to divide it the smallest number. Okay, for example, here. Yes, here this is the smallest number of the other subscripts, and yes, divided all of that numbers that's small. Okay, and then you will find how many you will find. Please, can you check here? I think for the carbon atom, this is the 1.75. For the hydrogen atoms, this is, I think, 2.5. Please, can you check that? And for the oxygen, only 1. And I don't write any number of the subscripts for the oxygen atom. Okay, is that right or don't right? Please, can you tell me? Always, still we have that small, still not whole number. Okay, these subscripts have to be whole number. Okay, have to be whole number. Yes, that's right. Okay. This is not the whole number, so I have to multiply with, if we multiply with the 2, that's carbon atoms mole will be 2.5. This is not the whole, so I have to multiply with that. This is the 4, okay, and then 4, and then 4 have to multiply it, and then this is the new empirical formula will be, this is C, carbon atom will be 5, and then the hydrogen, for the hydrogen will be 10, and then for the oxygen will be 4. Okay, and we get by this method, just outline here C5H10 and O4 is the simplest formula, and this is the empirical formula. Okay, this is the empirical formula. Don't forget that. The actual molecular formula may be equal, or some multiply of that. The empirical formula suggests, for example, multiply with 2. This is carbon 10 and hydrogen 20 and oxygen 8, and we can say like that. This is, if we want to multiply with 3, this is carbon 15 and hydrogen 30, and this is oxygen 12, and so on. To find the multiplying factor, we must compare the formula mass based on the empirical formula with the true molecular mass of the compound, and we can establish the molecular mass from a separate experiments like the others, and if they say us this is real molecular mass, if they said, yes, that's right, this is the real and empirical formula the same, we can say like that. And this is explanation of what I explained that here. Yes, that's right, this is the explanation, all of that. Yes, and other, yes, mass, percentage, composition of the compound, and assume 100 gram, and then gram of each element multiply with molar mass and moles of each element, calculate mole ratio, and you will find empirical formula. The empirical formula and real formula is very important example of for that subject. Yes, this is the example. This is so good example actually. Yes. What is that? This is dibutyl succinate, is an insect repellent used against household ants and roaches. Its composition is 62.58% carbon atom and 9.63% of hydrogen atom and 27.79% oxygen. It is experimentally determined molecular mass. This is the experimentally, okay? Experimentally determined molecular mass will be like that. This is 230. U is that means this is the molar mass, we can say molecular mass, or what are the empirical formula and molecular formula of dibutyl succinate? Because you don't know anything about that, the CX, for example, H, Y, and this is the O, Z. Okay, Z here. You don't know about that and that and that one. But you know the percentage of the carbon atom. And I said, you can think that the percentage is equal to gram. This is you can think that this percentage is the mass. Okay, and then for the carbon atom, if you want to find the mole of carbon atom, the percentage divided with the carbon atom atomic mass, and then you will find that one. And for the hydrogen, you will divide this hydrogen atomic mass and you will find that one. And for the oxygen, the same thing. This is the mass, you will think, and you will divide this oxygen atomic mass and you will find that oxygen. If you want to write here the carbon, 5 is 0.210 and hydrogen 9.55 and oxygen 1.737. This is not our empirical or molecular formula. That will be that's all of these mole have to be whole numbers. Okay, have to be whole numbers. So you have to divide the smallest numbers. This is the smallest number. You have to divide. Yes, small number, and here the smallest numbers you have to divide, and you will find here what is that. Right, we write first of all the tentative formula, and then we will pass the whole numbers and divide each of subscripts, you know that, of the tentative formula by the smallest subscripts, and you will find here the carbon, for the carbon atoms, this 2.99 approximately. That will be, yes, Mariam, that will be 3, we can think that. And for the hydrogen, yes, for the hydrogen, what is that? Yes, 5 point, yes, and then the oxygen only 1, but this is not the whole numbers. These are not whole numbers, so we can think that this is the carbon atom 3, because this is approximately 3, and for the hydrogen 5.5, we can think that, and the oxygen. And we have to multiply all of these subscripts with the 2, because we have not the whole number for the hydrogen, and if we multiply with 2 all of these atoms, and carbon will be 6, and hydrogen will be 11, and oxygen will be 2. This is, what is that? This is our which formula? This is our which formula? This is our which formula? Yes. What is the answer? This is our which formula? Please tell me. This is real molecular formula or empirical formula? Which one? Are you there? Yes, that's right. This is the empirical formula. This is not real molecular formula. If you want to find, they ask us, they say us, it is experimentally determined molecular mass will be 230 gram divided mole. But here we have to calculate that hydrogen and here oxygen. This is, we can take that carbon atoms 12, yes, multiply with the 6, and then here 11 multiply with the 1, and then for the oxygen 2 multiply with the 16, and then you will find this is the 115U. Okay, 115U, but you have that molecular mass. Experimentally, you determine that. So this is how many numbers you have to multiply that empirical formula molecular mass. Check here and check here. This is 115 and this is 230. Yes. If the molecular formula is, what is that? Yes, that's right. This is the empirical formula molecular mass, but the real molecular formulas will be 230. And what will our formula will be? Our formula. What is the our formula? Carbon. What is the X? What is the Y? And what is the oxygen for the Z? What will be these subscripts for the real molecular formula? Because they are found 230 gram divided mole molecular mass, but we have the empirical formula, and the empirical formula molecular mass 115 U. Yes, I am waiting. How many times? How many times these molecular formulas from the empirical formula? How many times? Yes, I am waiting. What is the Süleyman said the 2. Yes. What else? Because you know the molecular mass. Yes, that's right. Because if you multiply with these empirical formulas molecular mass, multiply with 2, and you will find 2.30 U. So you have to multiply with the 2 all of these subscripts. Yes, that's right, Mariam. Thank you so much. This is the X will be 12 and Y is the, what's that? This is a 22 and Z will be, what is that? This is only 2 and this is 4. Yes, this is our molecular formula. For carbon atom, 12, and for the hydrogen atom, 22, and for the oxygen atom will be 4. This is the simplest example of determine the percentage of from the determine this percentage from that molecular formula. Is that clear or not clear? Please again and again listen this example explanation, and then you can understand so clearly, because I am doing step by step actually. This is explanation of this example, and then this is your homework. This is sorbitol, sugar-free sweetener foods, and you don't know anything about the formula of this sugar-free sorbitol, and C, H, and O, they give you the percentage of these atoms, and you can think this is your mass, and you will do the same thing. The last example, for example, for the B, the chlorine-containing narcotic drug, pentaerythritol, chloral has CHO. All of these, be careful that all of these samples are generally organic compounds. And it is molecular mass will be 726 U, and then you will find the empirical and you will find the molecular formula. Okay, pentaerythritol chloral. Yes, naming compounds, organic and inorganic compounds. We will stop here, and then the next week we are gonna continue here. Okay, all of these examples, I think I wish these are the, you understand. And then any question about the others? Thank you so much, Miriam. The others, have you any question? Please check your OIS mails, okay? Thank you so much. Take care of yourself. See you later.